Murray, and I'll be presenting this video abstract on an exact synthesis procedure for minimum quality factor spherical wire antennas, which is based on an article co-authored by myself and my PhD supervisor, Ashwin K. Iyer. So the background for this work essentially is that small antennas are known to have very limited impedance bandwidths. And to that end, there are multiple rigorous spherical wave-based analyses which place bounds on Q in terms of Ka. Ka being a measure of electrical size, the product of the wave number, and the radius of the smallest sphere which circumscribes the antenna, and Q, which is a measure of inverse bandwidth, effectively. The best performing small antennas with respect to these bounds on Q are spherical in shape and usually only make use of electric currents. The goal for this work was to design an antenna directly from the spherical wave theory. The first steps were to just start with the definition of the spherical waves themselves, which are essentially a set of electric and magnetic currents defined over all of space. Then via equivalence, we could derive the electric currents that would flow on the surface of a sphere that would radiate only that mode. We then equated the radiated powers of the fields of these spherical waves and the dissipated powers of the circuits, which were first presented by Chu, the circuits, those being those circuits for the spherical modes also. We then related the spherical wave current amplitudes to the currents entering Chu's network. To derive an antenna design, we then took a general parameterization in spherical coordinates, and then we were able to relate this parameterization to the resulting current density, which would be on the surface of the sphere parameterized by W here. With this, we were able to derive a spherical wire shape, which prescribed direct control over the ratio of TM10 and TE10 mode amplitudes. And with this, we were able to design the antenna to provide a minimum Q based on the spherical mode theory. So the first of two simulations in the article, one is a thin wire antenna. So we ran simulations assuming thin wires, and we found they produced the minimum Q, shown in the plot in blue, and nearly the minimum Q when requiring circular polarization, shown in yellow. The plot is for the case of 60 arms, and the diagram is showing a case of 2 arms. We then took a look at maybe a more realistic design for fabrication. We went with an 8-armed tape antenna design with all the wires fed in parallel. And we can see here, looking at the Q normalized to the lower bound, that with the performance of the Q is quite low. So that concludes this video abstract. Thank you very much to the Transactions on Antennas and Propagation Media team for featuring our article.